Humans rely on biological photoreceptors that struggle when light disappears. In a blinding storm at night, our vision effectively drops to zero. But a self-driving car can navigate this exact same environment perfectly, steering itself through a completely invisible road. Autonomous vehicles accomplish this by relying on sensored fusion. They combine traditional cameras with LiDAR, radar, and thermal sensors. This creates a redundant, multi-layered model of the environment, allowing the vehicle's perception system to operate safely in conditions that render human eyes completely useless. Yet the foundation for this mechanical capability started with an attempt to copy biology. In the 1980s, neuroscientist David Marr proposed that the human brain processes vision in stages, starting with a basic sketch of visual edges before building up to full three-dimensional shapes. Early computer vision copied this blueprint directly. Engineers designed algorithms to convert light into a grid of numerical pixels, mirroring how our retinas use photoreceptors. But to achieve the real-time processing speeds we see today, machines had to abandon their human constraints and analyze the world through entirely different mechanisms. This animated diagram illustrates how convolutional neural networks, or CNNs, process visual data. The network uses a localized filter that slides over the image, analyzing a few pixels at a time. It identifies basic geometric edges first, stacking those layers step by step to eventually recognize complex objects. Because a CNN builds its understanding piece by piece, it struggles to grasp the overall context of a scene quickly. The processing layers have to get very deep before the network understands how an object on the far left of an image relates to an object on the far right. In 2020, researchers introduced the vision transformer. It treats an image as a sequence of data. Instead of scanning, the image shatters into fixed patches. Using global self-attention, it instantly connects every patch to every other patch, calculating their relationships all at once. By processing the entire grid at the same time, the machine captures the global context from its very first calculation. This allows it to understand complex spatial relationships across a flat, two-dimensional space immediately, rather than waiting to build them up layer by layer. Processing a flat image is only the first step. When a machine needs to navigate a physical environment, simply drawing a two-dimensional bounding box around an object fails to capture how much physical volume that object actually occupies in reality. To solve this, machines construct spatial models using LiDAR. By bouncing millions of laser pulses off surrounding surfaces, the system generates a dense map of floating data points, explicitly plotting the precise depth and geometry of the physical world. When LiDAR isn't available, researchers use neural radiance fields, or NeRFs. This technique takes a handful of sparse, two-dimensional photos and uses a neural network to calculate how light behaves, inferring the missing three-dimensional geometry between those flat images. Combining these methods allows a computer to generate and render volumetric environments in real time. The machine is continuously simulating the physical volume of the space it occupies. Translating flat pixels into physical dimensions makes the camera an active spatial reasoning engine. It calculates exact distances, anticipates physical collisions, and maps complex trajectories. Even with depth factored in, standard cameras have a severe efficiency problem. They record footage at fixed frame rates, repeatedly capturing and processing the exact same background data frame after frame, even when absolutely nothing has moved. Neuromorphic vision sensors solve this by mimicking the biological optic nerve. Instead of recording full frames, these sensors operate asynchronously, capturing only changes in brightness. A static background is ignored entirely, and only moving objects register as spikes of electricity. Eliminating that redundant data reduces processing time drastically. It yields microsecond latency, giving fast-moving drones and autonomous vehicles the reaction speed required to make split-second driving decisions. Machines also expand their perception past human limits through hyperspectral analysis. While our eyes are restricted to a narrow band of visible light, multispectral sensors analyze a massive range of wavelengths, from infrared to ultraviolet. This extended spectrum isolates AI-generated media. Deepfakes work by tricking the human brain's holistic understanding of a face, but hyperspectral analysis detects the synthetic pixel gradients and unnatural light signatures invisible to our eyes. By ignoring static noise and reading broader light spectra, Machine perception captures data that human biology simply doesn't register. For decades, the hardest limit on teaching these systems was humans themselves. Supervised learning required millions of images to be hand-annotated with text labels by human workers before the machine could learn to identify an object. In this diagram, we see the mechanics of self-supervised learning. Instead of relying on human tags, the model takes massive amounts of raw, unlabeled visual data and finds the patterns on its own, autonomously sorting the information into distinct logical categories. By comparing billions of raw data points, the system learns how objects relate to one another structurally and temporally. It stops memorizing localized pixel labels and instead builds implicit knowledge about how the physical world actually operates. Models that build their own internal logic by observing the world move beyond narrow task recognition toward a more flexible, general understanding of visual reality. If you want to see how these models are already being deployed, hit subscribe and join us for the next video.